We're going to fix that another time. We're going to fix that later. But right now, it seems like we've got this working. Chubby Dragon, what is my end goal in streaming? I have absolutely zero end goal with streaming. I'm just here to teach. I have no end goal. This is not going to be my career. I'm going to be working at a university as a professor. That's my goal. That's my only goal. So, yeah, there is no. I don't have an end goal in streaming like making it a career move or something. Okay, so back to the question of. Let's see. So the question was, why does the errors labeled data path take up so much space on that A5 chip, that Apple chip that we were looking at? So in order to answer this, it's probably good that we actually go back to the section on that chip. That way we have some reference. Listen, I'm going to enroll you guys to help me, okay? You guys are going to be my guides. I sound a little bit like Day 9. We're the same person. It's all a big ruse, right? He didn't get a degree in math. He got it in computer engineering. There's your fun fact of the day. Okay. So let's see. Listen, if you guys want to follow me on Twitter, or you're going to follow me on Twitch, or whatever you're going to do, you know, there's a donate button down there. But I want to let you guys in on a secret. I'm not doing this for the money. You guys don't need to donate. I will never put any of this content behind paywalls. This content is there for you guys, the younger generation, or for anybody out there that just wants to learn. None of this will ever be behind paywalls. This will all be free all the time. Okay, so let's look at where they talk about data paths. I passed it up here. They probably defined it earlier. Input, output. Okay. Through the looking glass, input, output, pixels, frame buffers, touchscreen, inputs, output, opening the box, the CPU. Okay, here we go. So here we're talking about the data path. So the data path performs the arithmetic operations, and control tells the data path, memory, and I/O devices what to do according to the wishes of the instruction. Okay, so let's see. I forgot who asked that question. Listen, I have limited windows. This is where a third monitor would help. Okay, here we go. And why so green? It's because, listen, no one's going to know who I am and what I do from why so green. So we're using engineering today. Okay, Yom Slinky, right? Why does that take up so much space? So that's, like it says right here, that's going to perform all the arithmetic operations and control. And the control tells the data path and everything what to do. So what we do in computers is we do a lot of math. That was originally why computers were made. And fundamentally, everything can be broken down into some kind of mathematical operation, be it something logical, like an and, an or, an exclusive or, some Boolean equation, right? So everything has to be broken down into simple units like that, because that's fundamentally what we make gates out of. So, or that's what gates build up. They build up so transistors build into gates. Gates can be represented by logical functions, and then our logical equations or Boolean algebra type equations, and then we can solve those to do anything that we want. So the reason why it takes up so much space is because, well, there's a lot of that to do. So, you know, if this is controlling all the arithmetic, well, we want to do a lot of arithmetic. I mean, we have to do all kinds of calculations, just like so this is going to have things like your ALUs, your arithmetic logic units. It's going to have any vector units or SIMD type units to do SIMD instructions. We'll talk about those later. But basically, if we want to do instructions on large amounts of data at the same time, What else? What else can we think of? Any kinds, yeah, so ALUs are typically, they contain multiple different things. And so you can think about what it takes to do different kinds of arithmetic operations. And then you also have to take into consideration that we're working with something that's referred to as superscalar architectures. So if you have seen anything about what a basic CPU pipeline looks like, a basic CPU pipeline is going to have different stages that perform different things. Now, what a superscalar processor basically means is that you take that design and you instantiate multiple of those same designs, basically stacked next to each other. So let's look up a picture of that. Let's look up a picture of superscalar architecture. Let's see. Maybe this. So that's super pipelined. Let's see, superscalar architecture picture. Okay. Let's look up modern CPU architecture. Okay, so I'm getting a lot of pictures there. Let's just look up a pipelined architecture. There we go. This is what I wanted to see. Okay, I'll put this on stream. So let me just go to this image, view image. Okay, so this is for something like a Mips. So here we have a basic pipelined Mips processor. So basically you can think of superscalar. If you took these and then you put 5 of them on a chip or something, then you would have this 5-wide superscalar processor, right? Because you would have 5 different things issuing at the same time. So that's what we mean by, that's why we need so much space here in this processor data path, because we don't just have to have the ALUs for a single or 2 ARM cores. We have to have it for, if it's a superscalar design, we need it for every pipeline in order to handle all of those instructions, right? So that's why we have that overall design, and that's why this takes up so much space. Also, if we look at arithmetic circuit cost as far as space, we'll see that if we want to do operations that are very expensive computationally, so when we talk about expensive computationally, we're really looking at division. Division is your, as far as arithmetic goes, and not including any kind of special function. So special function means square root, or let's see, what else? So square root is 1. Doing something like a log or a natural log is another special function that you can make a little section for. But overall, when we're talking about the generic functions, it's plus, minus, or add, subtract, multiply, divide. Divide takes up an enormous amount of area, and that's enormous amount relative to the other functions, and that's mainly because it's the slowest. It's actually orders of magnitude at divide's fastest architecture. It's orders of magnitude slower than it's orders of magnitude slower than add, divide, subtract, or sorry, add, subtract, multiply. Okay, so now that we've got that kind of cleared up somewhat, we can go ahead and we can start looking at where we left off last time. And that was something to do with technology. Here we go. Technologies for building processors and memory. Okay, so this is going to be interesting. So, like I said, if you guys, you want to check out more things that I'm doing, just as a heads up, I'm posting all these VODs are going to be on YouTube. The YouTube link's below. You can subscribe to that. I'm going to add more teaching content there. When I do more problem solving, that's going to be mainly on YouTube dedicated videos. So on here, I might do a stream here or there that's solving some problems depending on what people are asking for, but the majority of that is going to be pre-prepared content. Most of the long form content, like going through these books, is going to be on this channel though. And then there's a Twitter there where I'll find a use for that someday. Right now I'm just kind of going occasionally when I go live, but I have 10 people following me, so it's not extraordinarily. Am I doing the whole book? I'm absolutely doing the whole book. This is going to be the complete guide to intro architecture. Listen, I want to go through this whole book because I don't want anybody to have any questions at the end of this thing on intro computer architecture. I want everyone to master intro computer architecture at the end of this book. And I can't do that by just going over part of the book. Okay, before we get going, anything else? Do we need anything else before we get going? Awesome. I think so too. I think so too. And listen, if you guys have suggestions on things that would make the stream better, feel free to, shoot me a message, tweet at me, leave me a comment someplace. Listen, I'm just getting into this. I'm at that awesome point where I'm going to have the most interaction possible. So why don't we get started? So we left off at 1.5, which is technologies for building processors and memory. So right before this, we talked about the memory hierarchy, and we talked about how we communicate with other computers and why we want to communicate with other computers. And we found out that that was actually pretty interesting. So what we want to do now is we want to see, okay, so what are the building blocks that make these things? So let's start. So processors and memory have improved at an incredible rate. That's true. We talked about Moore's law earlier. Let's see if there's anything else interesting. So since this technology shapes what computers will be able to do and how quickly they will evolve, we believe all computer professionals should be familiar with the basics of integrated circuits. So let's look at it. So here we have 1951. This is 5 years after the first stored program computer, EDVAC. We have vacuum tubes. 1965, we have the first transistor. This was around the time Yale Pat was doing some, I think he did the first multi-transistor logical gate on a single piece of silicon in the early to mid 60s. Yale Pat's a famous professor from UT. He still teaches at UT to this day. I think he's like 78. Great professor. Then we have 1975. We have the first integrated circuit, if I'm not mistaken. This was at Texas Instruments, founded by Jack Kilby. And so right now, relative performance per unit cost. So all performance is normalized to the vacuum tube. So what normalized means it's basically divided by some baseline. So for vacuum tube, it's 1. So when we get 14 years later for the transistor, we're already at 35x. Integrated circuit, which is 10 years after that, we're at 900x. When we get to the very large scale integrated circuit, so this is VLSI. That's what when people talk about VLSI, they mean chip design. So in 1995, that's kind of the advent of more VLSI type work. And we're at 2.4 million times as fast as a vacuum tube, which, this is one of those things like when we start measuring horsepower for the space shuttle, it's not a very good unit at that point. So vacuum tube's not a good baseline at this point. But to show the overall scale of technologies over generations, it's fairly interesting, I guess. And then in 2013, now that we're getting into chips with the size of, like the Volta GPUs are, I think, 21 billion transistors. So that's when we get to this level of ultra large scale integrated circuits. So this we're getting to 250 billion with a B times faster than vacuum tubes. And so if you look at the relative size of this, you know, this is 62 years. But in 62 years, we improved performance by 250 billion x. Now, that's pretty good. I mean, I don't know. What do you guys think? I think that's pretty good. Okay. So let's continue on. So what is a transistor? So a transistor, we can think of that as an on-off switch, right? And so an integrated circuit, we're just combining dozens to hundreds of transistors into a single chip. So Gordon Moore, the person who Moore's law is named after, and Moore's law is exactly this thing right here. Gordon Moore predicted the continuous doubling of resources. So remember, doubling of resources, that's Moore's law. 250 billion% increase. Yeah? Wait, no. No, it's not 250 billion%. It's, wait, is it? Am I thinking about this correctly? So 100% increase would be 2x, right? But this is 250 billion x, not percent. Okay. So let's move forward. So when we're talking about lots of transistors into these later chips, we use very large scale for VLSI. So we have very large scale integrated circuit, VLSI. Neat. So some of these terms don't actually, you know, they're okay. They're neat context, but we're not learning too much here. Here we go. So now we get to learn something about the scaling of memory over time, right? So back here, early 70s, DRAM comes out. So we're at, 16K back in the 70s. We get up to about a meg in the 80s. We get up to 16 meg in the 90s. By the time we're hitting 2004, we're getting to 512 meg. To all the way to 2012, we're getting to 4 gig. And these are per DRAM chip. So this isn't like total memory or anything. This is per DRAM chip. And so this makes sense. This makes sense to us because we have this exponential scaling of Moore's law. Keep in mind that this graph is logarithmically scaled. Right? So we see the same trend in scaling of DRAM capacity as we do with transistor scaling. And so it's very easy to see why. Because in essence, what is DRAM? So DRAM is only a single capacitor and a single transistor. So if we half the size of all of the transistors, it makes sense that our capacity per unit area is going to double. So that makes sense to us. Okay, so let's continue on. To understand how to manufacture integrated circuits, we start at the beginning. So chips begin with silicon. Okay? And we use silicon because it does not conduct electricity well, so it's a semiconductor. So here's a fun fact. Can anyone tell me why or how we would define a semiconductor, right? So it says that it doesn't conduct electricity well, but if we're going to more rigidly define what a semiconductor is, how would we go about doing this? Can anyone answer that or have any ideas? So keep in mind what a conductor is and what an insulator is. So a conductor is going to have almost no resistance, very, very little. An insulator is going to have extraordinarily high resistance. Think about it as infinite. Okay. It has higher resistance than a conductor, but less than an insulator. Yep, that's exactly right. It's pretty arbitrary. It's basically just something in that middle between having no resistance and some resistance. Yeah, exactly that. You know, it's a lot of people get tripped up. It's like, oh, a semiconductor, it means something super special. Nope, it just falls within that region. That's it. Okay, so moving on. So, with special chemical process, it is possible to add materials to silicon that allow tiny areas to transform into one of three devices. Okay, so when we talk about adding materials, when we talk about adding materials here, we're talking about a process called doping. Yep, that's right. That's doping. So, yeah, that's how we give it, you know, so we're basically putting on like protons or electrons, and we're giving some charge to it by using, because silicon itself, the lattice that silicon forms is very stable. We can play around with that though in order to make p-type and n-type. Like all the cool kids at school, that's right. Whenever you see cool kids in school talking about dope, they're talking about semiconductors. Tell your friends. Okay. So let's see. So excellent insulators from electricity. Okay, so here's what we can make out of semiconductors. We can make excellent conductors using microscopic copper or aluminum wire. We can have excellent insulators from electricity, like plastic sheathing or glass. And then areas can conduct or insulate under specific conditions as a switch. So this is where we're using the semiconductors for. So transistors fall into the last category. So this category of they can either conduct or insulate under specific conditions, and that's usually based upon how we're applying voltage to these devices. So a VLSI circuit then is just billions of combinations of conductors, insulators, and switches. So basically what we're saying is the only thing that we're saying right here is that we can make all these complicated circuits with just a bunch of switches. So it's a little bit on the process technology. So it starts with a silicon crystal ingot. And so basically what happens is you have a bunch of molten silicon. You place a little piece of that pure silicon that you want into that molten silicon, and it gradually lifts up very, very slowly. And that's right, which looks like a giant sausage. And so it gradually pulls up, and all the crystals kind of bond onto that. I forgot what it's called. It's that initial, like a seed crystal that you put on there at first, and it pulls it up, and all the other crystals, so the molten silicon attaches in the same crystal-like shape. And so that's how they get these giant pieces of silicon out. And so an ingot is finely sliced into wafers. And so wafers are what we do doping on, right? That pure silicon. All right, and it looks like, yeah, Lev posted a video in chat. That's a great video. That's actually a video I watched when I took a semiconductor devices course. Old video. It's an oldie but a goodie. So they go through different processing steps, and this is in a place normally called a fab. That's where they fabricate things, as it implies. Let's see, anything interesting? You put chemicals on it, creating transistors, conductors, and insulators. Today's integrated circuit contains only one layer of transistors, but may have from 2 to 8 levels of metal conductor, separated by layers of insulators. Okay, interesting. A lot of this stuff is at a lower level of abstraction from what I work on, but still fairly interesting. And here we have a little diagram. So we have this giant silicon ingot that they say looks like a giant silver sausage. Interesting. Then they slice it into these blank wafers. So then whatever pattern we want, or whatever dies we're making. We imprint these into the area of this wafer. This goes into a wafer tester. So this is where we test to see if what kind of yield we got out of our processing or out of our fabrication technology. So if we get a bunch of errors, we have a very low yield. If we get very few errors, we have a very high yield. So we're happy. So like I said, they test it, and they cut them up. And so here we have the tested dies, and then they bond the die to a package. So this is basically mounting. Then they test the entire part. They get rid of the parts that don't work, and then they ship them to customers. So this is basically from silicon to, your Ryzen CPU, your AMD APU, your Intel i7, your i9, all your i-series processors. They all start like this. Every integrated circuit goes through this process. Okay. So here we go. Like a single microscopic flaw in the wafer can cause something to fail. And then these defects, okay, so they're just calling them defects. The patterned wafer is then chopped up or diced into these components called dies. So that's what we call those little the individual chips after we separate them from that big circle piece of that big wafer that we have originally. 20 to 40 processing steps. That's like all the actual making of the chips, but not really necessarily to know for this stuff. Yeah, absolutely. If I had more background in semiconductor manufacturing, I could describe what those steps are going to be, but a lot of it's going to be doping, and then you have to apply mask I'm not going to get into it because I'm going to make a I'm going to make a joke of myself. Oh yeah, what's the Intel TikTok meme? I don't know what the Intel TikTok meme is. That's a good question. Intel TikTok explained. What is that? Technology terms, TikTok typically refers to Intel's model of releasing new processor families each year, with the tick applying the processors fabricated on a smaller die shrink, and the talk representing processors that is based on a new processor microarchitecture. Okay. I mean, that seems like a fairly reasonable explanation. I don't know how long ago this is from, but so okay, this is on Intel's site. How old is this? I mean, this has 14 nanometer 3D transistors on here, so okay, so this is true. So they still do this TikTok thing. So it looks like, so in tick, no. Okay. So let's see. In tick, they are within a technology, and they move to a new microarchitecture. Okay. And then in talk, they're within that same microarchitecture. Oh, wait, no. Sorry, tick, they move to a new process technology. So in tick, they're in 45 nanometer now. In tick here, they're in 32 nanometer. In tick here, they're in 22 nanometer. In talk, they're within 45 nanometer still, but they move to a new microarchitecture. So all they're changing in talk is the microarchitecture, and all they're changing in tick, they're leaving the microarchitecture constant, but they're changing the process technology, so they're using smaller transistors. Okay. Hey, I learned something new. That's pretty neat. I didn't know that's what that was. Okay, neat. Thanks for sharing that. So let's see. So the individual rectangular sections that are cut from the wafer are known as die. So that's before they're put in packages. Okay, so here they have a picture of the Intel Core i7 before it's cut up. That's pretty interesting, right? I think that's pretty cool. So this is what you're paying all the money for. Imagine how much this is worth. This is worth a lot of money right here. That's a 100% yield wafer. That's pretty darn good. I don't know how reliable their process technology is. I don't know what good is as far as process technology yield. So yield is just the percentage of good dies from the total number of dies on the wafer. Okay, very simple concept. So if we have 100 dies on a wafer and 5 are bad, we have a 95% yield. Pretty simple. Okay. Moving on. So the cost of an integrated circuit rises quickly as the die size increases, due both to lower yield and to fewer dies that fit on the wafer. So that's likely an issue with GPUs now. So Volta's a 21 billion transistor chip. Now that's going to be a pretty darn big chip to fit on a wafer. So you're going to have to make sure that your process technology is spot on so that you're not getting in low yield and you're barely pushing out any chips. Okay. Yeah, but the 3 new recent architectures, we've been stuck at 14 nanometer, so they're just calling it optimizations. Yep, sure. Yeah, Intel's struggled recently with pushing to 10 nanometer. I think they want it to be 10 nanometer. They're behind on getting to 10 nanometer, but everyone's behind getting to 10 nanometer. Volta was also supposed to be in 10 nanometer. If you look at their original roadmap, their plan was to push Volta out at 10 nanometer, but I think they got to 14 as well. Okay. Interesting points. Interesting points. Okay. So, moving on. So the cost of an integrated circuit quickly rises as the die size increases, and so this is what we said previously, because you can fit fewer on there, and then if you have one go bad on there, it's a larger percent of your yield. Let's see. Once you've found good dies, so once you've done all the testing, they are connected to the input and output pins of a package using a process called bonding. So the chips that you actually have on your, when you look at all the pins on the bottom of your processor, on your processor, or for, any of those little black little chips that look like bugs, that have like the 6-pin or the 12-pin or the 20-pin chips, and the little dip packages, the dual inline package, or sorry, the dips or dual inline packages. If you look at those, then if you look at those, the actual silicon in there is very, very small. It's tiny. And so they have to do these little tiny wires that connect to each of those pins on the inside. So if you were to open up those little, those things, it's not, a lot of that is just empty space in there. So this is, this is their basic calculation. So the cost per die is basically, how much does it cost to make a wafer? And then how many dies can you put on a wafer times your yield, which is a percentage of how many of these dies are good. And so that means dies per wafer is, you can see how you get this, and then you'd see how you find yield out of that. So it's just a lot of rearranging of terms. Okay, so yeah, the second one's an approximation, like it says. Let's see, anything else? Okay, no, this is fairly straightforward. how we find cost per die, dies per wafer. And so, like it says down here, where does it say that? The second one. The second is an approximation since it does not subtract the area near the border of the round wafer that cannot accommodate rectangular dies. So yeah, like I said, these things are pulled up by the seed crystal, so you end up with this giant silicon cylinder. So it's not like a rectangle where you can completely use all the area effectively. So it doesn't include that. So this wafer area is actually smaller than this approximation. Okay, and then your yield. Sure. It's just empirical observations of yields at integrated circuit factories with the exponent related to the number of critical processing steps. Okay. And so like this is defects per area. So basically if you're going to have, do they cut it into a rectangle? Do they cut what into a rectangle? So what happens is you have a circle. Very poorly drawn circle. And then when it's going through its processing steps, you wind up with something like this. So all of these right here on the edge, you can't use these because they're non-rectangular. Because chip designs are rectangular. So your actual yield is only these internal ones, which are these rectangles. Yeah, people don't manufacture triangular integrated circuits. They're all rectangular, square. So yeah, all these ones with curves, those are just chopped off. And so they try to minimize that. So we can go back up and look at the i7. And so we see that we have all of these right here. So, these aren't actual i7 processors. These aren't actual i7 processors. These aren't actual i7 processors. These aren't actual i7 processors, and the same for all of these. Okay. Okay. So let's move on. So let's see. Check yourself. With high volumes, the manufacturing process can be tuned to a particular design, increasing the yield. Okay, which of the following are reasons why a chip made in a high volume should cost less? Okay, with high volumes, the manufacturing process can be tuned to a particular design, increasing the yield. Sure. So number one is going to be true. And so can anyone tell me why it's going to be true? I'll just a quick 1 word, 2 words is all you need to answer this. Okay, I mean I can just go ahead and answer it. So the reason why is if a manufacturing plant. So it's asking which of these reasons why. So it's basically like which of these are. So it's pretty much true false. So the question is more of why would this do it, or would this not do it? So a chip made in high volume should cost less. Which of these are reasons why? So this one says the chip should cost less when made in high volume because with high volumes, the manufacturing process can be tuned to a particular design, increasing the yield. That's true. If we have a fab only working on a single chip, they can optimize how they make that chip. That's why when you see the graphs of Intel's foundries for making their chips, we see that their yield is increasing over time. It's because they're getting better at their process technology. Okay. It is less work to design a high volume part than a low volume part. So this isn't any reason why a chip made in high volume should cost less. And this is also not necessarily true. So you can think of a reason why this wouldn't be necessarily true. So one reason why this might not be true is because if we have a low volume part that doesn't say anything about the complexity. Same thing with the high volume part. It doesn't say anything about the complexity. Yield is determined by complexity, and same thing with cost. Cost is determined by complexity and then brought down by your total volume that you're making. If you make a large volume, you're generally selling and buying in bulk, selling in bulk. So the masks used to make the chips are expensive, so the cost per chip is lower for higher volumes. Yep, that's correct. 4, engineering development costs are high. That's absolutely true. And largely independent of volume. That's also true. Thus, the development cost per die is lower with high volume parts. That's correct. Gallium chips. Gallium arsenide, yep. High volume parts usually have smaller dies, so this is just speculation that doesn't make sense. It depends what you mean by high volume. I don't know what they mean by high volume here. So I'm just going to go ahead and say that that is not a reason. Okay, so we got that down. We understand that. So now we can move on to something that's way more interesting. And if you decide to do computer architecture research, this is your bread and butter, understanding performance assessment. Okay, so let's see. So performance. Accessing the performance of computers can be quite challenging, or assessing, sorry, not accessing. Assessing the performance of computers can be quite challenging. The scale and intricacy of modern software systems, together with a wide range of performance improvement techniques employed by hardware designers, have made performance assessment much more difficult. So there's a lot of abstraction now to get through, so it's hard to tell what the underlying architecture is doing. Also, fun fact, a lot of times companies intentionally don't disclose their architecture because they use things that they shouldn't, which means that there's patent infringement and they use ideas from research papers without telling anyone. So that's a fun fact. Okay. When trying to choose among different computers, performance is an important attribute. Yeah, that is a yikes. The great thing is when they get caught, though. When they get caught, it's absolutely fantastic. Because then they get sued and then they try to say, no, we didn't infringe on the patent was invalid, and then they lose immediately. There's never a harder shutdown because it's indefensible. Because the time it takes to get a patent is so incredibly enormous, and the rigor that it takes to get a patent, you have to find a really hard way to prove that it's invalid, and that's not going to happen most of the time. So basically this is just saying that we want to know how to measure performance because it's important in order to tuning our architectures and selecting a computer. And so they're going to describe different ways in which the performance can be determined. Okay. So what do we have here? We have defining performance. So before we measure performance, we have to define what we mean by performance. So although the question might seem simple, an analogy with passenger airplanes shows how subtle the question of performance can be. So here's a figure, and let's see if we can just look at the figure and figure this out. So we have 4 different planes. We've got a Douglas DC-850, a Concorde, we've got a 747, and we have a 777. So here we have a lot of different metrics to look at. So we have passenger capacity, we have cruising range in miles, we have cruising speed, mile per hour, and then we have passenger throughput, which is passengers per mile per hour. So, from immediate inspection, it seems like, wow, the Douglas DC-850 is terrible. Look, we barely get any passengers, per passenger. We barely are moving anybody. We have very, very, very low throughput. However, we have to consider something else. What if our only goal is to go the maximum distance? What if we don't care about how many people we're bringing? We just want it to go the maximum distance. then this metric doesn't matter. And the same thing for some of these other metrics. So if we only care about throughput, right? So the number of passengers that we get for a certain distance with a certain speed, we want the 747. And then if we're looking at these other two, we're really trying to find a balance between the two, right? So that's what we're saying here. We're saying that it's not apparent to see what architecture is better because it depends on what goal we're targeting. So when we start looking at architectures and optimizations, we have to define ahead of time what are we setting out to do, because we have to be realistic. We can't make everything better. We have to say, well, we can make these things better with perhaps a slight cost to something else. Okay. So here we go. Let's suppose we define performance in terms of speed. This leaves two possible definitions. You could define the fastest plane as the one with the highest cruising speed, taking a single passenger from one point to another in the least time. If you were interested in transporting 450 passengers from one point to another, however, the 747 would clearly be the fastest, as the last column of the figure shows. So basically, it's exactly what we kind of went over. There's a lot of different ways that we can measure performance. And so this is kind of what we're going to define down here, and a couple metrics that are very, very common. So if we're running a program on two different desktop computers, you'd say the faster one is a desktop computer that gets the job done first. However, so we'll just highlight that. So desktop, we're looking at job done first. But if we're running a data center that had several servers running jobs submitted by many users, you're saying the fastest computer was the one that completed the most jobs during the day. So here we're taking more of a throughput approach rather than a latency approach. So by throughput, I mean getting the most work done in per unit time overall. And by latency, I mean the response time. So how fast it got just a single task done, the single task execution time. So as an individual computer user, you are interested in reducing response time. And this is something that regular CPUs are optimized for. They're optimized for response time, otherwise known as execution time. Yeah, so also referred to as execution time. Data center managers often care about increasing throughput or bandwidth. So throughput or bandwidth, we can say, are interchangeable terms. And this is something that GPUs are optimized for as well. So that's a big difference between CPUs and GPUs. It's either throughput optimized or execution time optimized or latency optimized. So response time, execution, or latency, that means we're talking about CPUs. If we're say throughput or bandwidth, that means we're talking about GPUs or data centers. Okay. So here we go, execution time. That's complete a task completely, so disk access, memory access, I/O, OS overhead, CPU execution time. Bandwidth means it's just a measure of performance. It's the number of tasks completed per unit time. Okay, so here's an example. So do the following changes to a computer system, or do the following changes to a computer system increase throughput, decrease response time, or both? Replacing the processor in a computer with a faster version. So if you decrease response time, almost always improves throughput. So decreasing response time almost always improves throughput. Okay, yeah. Hence, in case 1, both response time and throughput are improved. That makes sense. In case 2, which is adding additional processors to a system that uses multiple processors for separate tasks, for example, searching the web, so your single application that gets running doesn't go any faster because it's still on the same type of CPU, and that single CPU is taking just as long, but you can do more individual things at the same time, so it's more parallel. And so that we're just improving throughput. Okay. So when we talk about performance, it's important to understand these metrics. When we say performance X, this means 1 over the execution time of X. So that's how we relate those two things. Okay. Then, so that means that we have this performance metric of X versus some performance metric of Y. That means if we were to substitute in this 1 over execution time, that means 1 over the execution time of X must be greater than 1 over the execution time of Y. Basically saying the execution time of Y must be greater than X for X to be better performance-wise. So, you know, we're defining a lot of different ways to write the same things here. It's important that we understand how we can manipulate these performance metrics. So in discussing computer design, we often want to relate the performance of two different computers quantitatively. We will use the phrase X is n times faster than Y, or equivalently, X is n times as fast as Y to mean the performance of X over the performance of Y is equal to n. So this means the performance of X over the performance of Y is the same thing as the execution time of Y over the execution time of X is equal to n, this term that is, you know, some scalar value of, you know, how many times faster Y is than X. Or it could be slower, so slow down is the opposite of speed up. Usually we're concerned about speed up unless we're intentionally slowing down something. So yeah, a little thought on relative performance, a little example. And so we can kind of work through this. It has the answer right here, but we can still work through it. So yeah, so we have, if computer A runs a program in 10 seconds, and computer B runs the same program in 15 seconds, how much faster is A than B? So we use the same performance metric of performance A over performance B when we want to measure how many times A is, so we know that A is n times faster, so we use this equation, execution time over execution time. So B is 15, A is 10, 1.5x faster. So we get a modest increase. That's pretty good. Sometimes you get papers that have giant 937 times faster, which is fairly interesting. And then, you know, some more rearranging, performance of A over the scaled performance to get from B to A is going to be performance of B. Okay. Okay. So I think we understand most of this pretty well. So basically, we have this performance defined as 1 over the execution time. Then we can relate two performances together by substituting in this execution time. We define some scalar value n that's going to mean how much faster is the performance of X over the performance of Y. And then we can substitute in for execution time in order to find this in many scenarios if we don't have these performance numbers, which oftentimes we just have the execution data. Okay, so measuring performance. So how do we actually measure performance? What's a good metric to measure? Does anyone know what we typically use as our metric for performance? So a lot of times the metric that we use, memes per second, is, yeah, it's close. It's usually IPC. So IPC stands for instructions per clock cycle. Or they use CPI, which is just the inverse of that, clock cycles per instruction. So those are two very common when people are talking about performance. But I like memes per second. That's pretty good. I like that. So let's get into measuring performance. So the most straightforward definition of time is we'll use wall clock time, response time, or elapsed time. Okay. So that's what we mean when we're talking about execution time. So we're just using some standard value that we can get at many different points in time, and we're using that as a way to measure out our we're just using, it's just execution time. I don't need to, I'm getting overly complicated explaining that. Okay. So here we define different things. So CPU execution time, which recognizes distinction, is the time the CPU spends computing the task. So the CPU time is literally just the computational time. The user CPU time is this time spent in the program itself. And then the CPU time spent by the operating system to do things is the system CPU time. So from here it looks like we have the CPU execution time, and the system CPU time is going to combine together and give us the user CPU time. Okay. That makes sense. For consistency, we maintain a distinction between performance based on elapsed time and that based on CPU execution time. We will use this term system performance to refer to elapsed time on an unloaded system, and CPU performance to refer to user CPU time. And we will focus on CPU performance in this chapter, although our discussion of how to summarize performance can be applied to either elapsed or the other. Okay, so we're basically saying that, either way we can calculate similar numbers, but it's important that we strictly define what we're saying so there isn't confusion. Okay. So here all they're saying is that different programs have different bottlenecks, and it's important to understand where those bottlenecks are. So some applications rely on I/O. What else? Yep, they're just finding performance bottlenecks. Okay. So although as computer users we care about time, when we examine the details of a computer, it's convenient to think about performance in other metrics, and particularly clock cycles, or ticks, or clock ticks, clock periods, clocks, or cycles. So there's 1,000 ways to define this and talk about this. But typically, I usually say cycles or clock cycles. I usually don't say ticks or clock ticks. Maybe occasionally I'll say ticks, actually. Okay. So designers refer to the length of a clock period as a clock cycle. So that's what we're talking about. So let's see if we can look at these check yourself questions real quick and see if we kind of understand what they're talking about. So suppose that we know an application that uses both personal mobile devices and the cloud is limited by network performance. For the following changes, state whether only the throughput improves, both response time and throughput, or neither improve. Okay. So our bottleneck is network performance. That means our I/O between our personal mobile device, and that means our personal mobile device is running a lot faster than the cloud can keep up with us as far as network connectivity goes. So an extra network channel is added between the personal mobile device and the cloud, increasing total network throughput and reducing the delay to obtain network access. And then B, the networking software is improved, thereby reducing the network communication delay but not increasing the throughput. C, more memory is added to the computer. And then 2, the question 2, computer C's performance is 4 times as fast as the performance of computer B, which runs a given application in 28 seconds. How long will computer C take to run the application? Okay. So right here, we can go ahead and look at an extra network channel is added, and we're reducing latency to get network access. So that means we're improving this. So that means both response time and throughput improve because we're adding another network channel so we can get more bandwidth. And then it's also saying that it's also reducing the delay to obtain a network access. So we're improving both. But in case B, the networking software is improved, thereby reducing the network communication delay. So that means we're only improving latency. And then C, more memory is added to the computer, we're not improving anything. So if we say that network is our bottleneck and we improve something that improves the latency on the mobile device, the PMD, personal mobile device, that means we're not going to be improving our throughput or latency because our bottleneck isn't at the mobile device. Our bottleneck is still at the network. Okay. So let's move on. So we get those. So we got the key ideas. We got any questions? Any questions? Anybody have any ideas or questions or things that they want to discuss before we move on? We only have a couple sections left in this chapter. Because a lot of this are kind of examples that we can briefly go over. Okay. So let's go ahead and move on. So let's get to CPU performance and its factors. So when we're talking about CPU performance, we're generally referring to something like this. So we're generally looking at CPU execution time, which is calculated by the clock cycles. So this is what it takes to do each instruction. Each instruction is usually done in for a single cycle processor. Basically, what you can think is what your goal is should be about an instructions per clock cycle of 1. That's like a very naive baseline. You can do a lot better than that, but it's a naive baseline. So you can also represent this as CPU clock cycles for a program over clock rate. So here we just have 2 metrics that we can look at, which is fine. We can kind of move past that. So here we have an example, and it says our favorite program runs in 10 seconds on a computer A, which has a 2 gigahertz clock. We are trying to help a computer designer build computer B, which will run the program in 6 seconds. Okay, so we want to improve the performance by 40%, right? So the designer has determined that a substantial increase in the clock rate is possible, but this increase will affect the rest of the CPU design, causing computer B to require 1.2 times as many clock cycles as computer A. What clock rate should we tell the designer to target? Okay, so we've got a penalty that we're increasing the number of clock cycles by 1.2x, but we can increase the actual frequency of the clock by an arbitrary amount. So this is entirely unrealistic because, well, actually it's a 2 gigahertz, so you do have a large window of improvement. So let's see what they do. So here they have CPU time, and they define that as your clock cycles over your clock rate. So that makes sense. They plug in their numbers. Then they do 2 times 10 to the 9th, which is 2 gigahertz, which is in the cycles per second. Then they get the CPU clock cycles of A. So that's going to be 10 seconds. That's the original running time. Times 2. Times 2 times 10 to the 9th cycles per second is equal to 20 times 10 to the 9th cycles. Okay, so this is their original number of cycles they take. Then the CPU time for B, you're going to have 1.2 times as many clock cycles as A. So you just use the same equation, but this time you have to scale it up because it says you're incurring this penalty. Then this time you're doing it in 6 seconds. Then we solve now for clock rate. Here we had the clock rate of 2. Here we're finding it. And so then we can shuffle some things around, and we find that we need a 4 gigahertz clock in order to improve the performance by 40%. So to go from 10 seconds to 6 seconds, we need a 40%, or we need to double the frequency. So that's a pretty steep penalty, really. As far as power goes, you're going to have wild power increases if you're doubling the frequency like that. That's a very tough thing. So let's look at instruction performance. So the performance equations above did not include any reference to the number of instructions needed for the program. However, since the compiler clearly generated instructions to execute and the computer had to execute the instructions to run the program, the execution time must depend on the number of instructions in a program. So one way to think about execution time is that it equals the number of instructions executed multiplied by the average time per instruction. Therefore, the number of clock cycles required for a program can be written as CPU clock cycles equals the instructions times the average clock cycles per instruction. Now, this is something where when they're averaging this out, hey Uncle Bill, how's it going? So when they're averaging this out, they're getting rid of everything like stalls related to dependencies between instructions. This is just saying, okay, so sometimes we get instructions that run very quickly. Sometimes we get instructions that run very slowly. So they just do an average. And this is a pretty good approximation. This is a classic thing to do. And so this is the term clock cycles per instruction, or CPI. And then it's eventually we'll get to the inverse of it, which is IPC, which is instructions per clock cycle, which is a metric typically used. So here they have it. We've got a simple example. We can go ahead and skip over this though. This is pretty simplistic. So a classic CPU performance equation, or the classic. We can now write this basic performance equation in terms of instruction count. So our CPU time is going to be our instruction count times the number of clock cycles per instruction times our clock cycle time. And so since we can define clock rate is the inverse of clock cycle time, we get CPU time is instruction count times CPI over clock rate. So this is basically the gold standard formula that we use for CPU performance. So yeah, instruction count, they have another definition here. It's just the number of instructions executed. So a lot of these formulas are going to reoccur throughout this series and throughout us going through this video. Alright guys, if you haven't, just in case there's anyone new here, I will be posting all these VODs to YouTube. It's in the link below. If you want to know when I go live and start teaching this, I typically do it in the evenings. This is a particularly late night where I'm doing 2 streams, but that's because I'm a Friday, or because it's a Friday today, and I felt like being a little more generous. So, you know, I figured I spend some extra time with you guys. So, let me do a little bit of quick advertising while we continue on with our wonderful, wonderful stream. Okay, so moving on. So comparing code segments. So oftentimes when we write code, one of the things that we run into is that we have classes of instructions that take different numbers of cycles to complete, and this may be because of the type of instruction. This also may be because of dependencies between instructions, but it's something that we should particularly keep in mind. So here we have instruction classes, and so this just depends on how our pipeline is laid out, how quickly each of these gets serviced in our designs. Okay. So the big picture here, this is what we're mainly concerned with. So this shows a basic measurement at different levels in the computer and what is being measured in each case. We can see how these factors are combined to yield execution time measured in seconds per program. So time is just seconds per program, so this is just execution time. And we're breaking this down as instructions per program times clock cycles per instruction, seconds per clock cycle. And we see that we're doing this, everything has a dependency on the previous thing. So clock cycles is going to cancel out, instructions are going to cancel out, and we get seconds per program. That way, depending on what metrics we have captured, timing is everything, that much I know. Absolutely. Timing is one of the most important things, and especially in digital electronics. All right, you got to go. Hey, have a wonderful night. I hope you learned something. Okay. So let's see. So here we have, so here we just have a table basically defining each of these things. Again, they really like to define every single one of these terms over and over. I guess it's good practice. They want you to get it in your head. Okay, so how can we determine the value of these factors in the performance equation? So we can measure the CPU execution time of running the program. Okay, so here we're just kind of figuring out how we can get these numbers. So we can use hardware counters. That's a good way to get these numbers. You know, there's a lot of tools within the so within processors themselves, they build in a lot of tools so that you can get very, very accurate timing data for executing your programs. And this is done as a very nice utility. Now, there's some security implications to this as far as side channel timing attacks, but for the most part, a lot of people use these to figure out how fast their program's going and really try to tune their program to work even faster. So there's actually, in x86 processors, there's instructions, I think they're like RDSC or RDTC instructions, and basically they are sub-nanosecond, so getting into picoseconds. They're sub-nanosecond precision timers. And so you're able to get such accurate timing information from those things. Okay, so let's see. So here they're kind of going over the dangers of if you only pick a certain type of performance metrics, you may forget about, or you may miss out on the actual root cause of some issues, or you may design around something that isn't actually there. Okay, so instruction mix. So it's very important that when you're looking at how a program is running, that you understand what types of instructions are being executed. So let's say you are running a program that is 90% branch instructions. So this would never happen, but let's just say, just for the fun of it. Or let's say something more realistic. Let's say it's, 50% arithmetic instructions, but only 10% loads and 10% stores, and so we're at 70, and then 30% branches, right? So if we were to focus on loads and stores, that's only 20% of all instructions. So if we make loads and stores a lot faster, we're making only 10 to 20% of the program faster. However, if we focus on the arithmetic part, that is 50% of the instructions, that means 50% of all instructions we're speeding up. So that's where we should be targeting first. So that's why it means we need to understand this instruction mix. Okay, so understanding program performance. So the algorithm. So the algorithm is going to affect instruction count and clock cycles per instruction. So if we write a very bad algorithm, oftentimes we're going to be doing a lot of unnecessary steps. So we're going to be adding a lot of instructions. So, and how does it affect CPI? So if we have an unfavorable algorithm and divides are, say, the longest arithmetic operation to perform, maybe divides can be replaced in your algorithm with multiplies in some clever fashion. So in the naive algorithm, you're going to be doing longer latency instructions. So you're going to have a higher CPI, where remember CPI is clock cycles per instruction. Okay, so the programming language, same kind of deal. That's fine. We can understand that. The compiler, same kind of deal. And you can read these on your own time, but I'm not going to get into them too much right now. There's a lot of parallels between these three. So once we get to the ISA, this is where we get instruction count again, but also clock rate. So this is where we start to see another thing be affected. So the reason why it affects why clock rate is affected here is because now we're actually talking about the architecture. We're actually talking about what's going down deep inside the processor. And so, if we make design decisions here at a hardware level that influence how fast we can run this clock. We can't run a clock faster than we're able to, say, complete some basic part of the pipeline, because then we're going to lose data someplace in the middle. Okay, so let's see. All right, so I think this might be the final section of Chapter 1. And this is the Powerwall. So now we're going to talk about why we've seen so much about CPU architecture recently, as far as Moore's Law stopping, and as far as, we can't rely on Moore's Law anymore to make faster processors. Frequency scaling is going away. And also, how are we going to power these chips? These chips get so hot now. We can't give them the power that they want, because they're just going to overheat. So here we see a very interesting trend. So here we see that along with Moore's Law scaling, we see, scaling with clock rate, we see this fairly gradual increase. However, we see this big spike in power. And so this is a very interesting thing to note, and we'll learn about this in a more advanced computer architecture lecture. And so the main reasoning behind this is that once we look at what governs power usage, we see that if we double the frequency, power is going to explode in the system. It's not going to increase linearly. It's not going to increase by some scalar factor. It's going to shoot up so much, which has really led to this trend lately, since like post roughly the Pentium 4 days. So Pentium 4 was, Pentium 4 had problems, man. Pentium 4 had problems. But we've seen this trend towards low power designs. And we've seen that your frequency has remained, fairly constant. Between 2004 and 2012, or let's do 2001, we've only increased about 1400 megahertz. So this is not great. This is not great as far as frequency scaling goes. However, this doesn't mean that performance hasn't improved. There's a lot of optimizations inside that have made things better. So, although power provides a limit to what we can cool in the post-PC era, the real valuable resource is energy. So for mobile devices, that's the case. So for personal mobile devices, we care about battery life. And I'm sure everyone here is probably in agreement there. I don't know if there's a good smartphone today that has a really good battery life. Nothing that compares to, back in the day. This is the real old me talking. Or I'm not even old, but we go back to the Nokia phones that you didn't have to charge for a month. I don't even think that's an exaggeration. I think you could get away for like a month without charging your phone. Okay. So the dominant technology for integrated circuits is CMOS. Like I said earlier, in the previous video actually, in the previous stream, that's complementary metal oxide semiconductor. So this just means, by complementary, they mean they have both NMOS type transistors and PMOS type transistors on the same substrate, the same silicon. Okay. So for CMOS, the primary source of energy consumption is dynamic energy. So that's going to be your switching energy. So the energy that it takes to change from a 0 to a 1 or 1 to a 0. So it's not the static energy, it's the dynamic energy that's the main issue. So dynamic energy depends on the capacitive loading of each transistor and the voltage applied. So there's a lot of work that gets done on trying to lower this capacitive loading that goes on. So the equation is the energy of a pulse during a logical transition, so 0, 1, 0 or 1, 0, 1. So this is basically a clock cycle. You can think of it. So you have a little bit of a 0, 1, 0, or you're at the tail end of a 1, 0, and then you get to another 1. Okay. So that's what they're talking about here of pulse energy and where they're getting this from. Then they relate this to power here through this equation, and they play around with it some more. Okay. So a lot of the nitty-gritty details of this are fairly straightforward, and you can look at it some other time. But we're really caring about the big ideas here. So frequency switched is a function of the clock rate. So what we mean by that is, so the clock rate comes in, if you don't know what a clock is, clocks are what drive everything in the system. So every action happens on clock edge in digital electronics. So in analog electronics, this is not the case. In digital circuits, in digital design, everything happens on what's known as an active edge of the clock. So that means everything gets triggered by some common clock. So that's why they say the frequency switch is a function of the clock rate, because that's when things are getting updated. The capacitive load for per transistor is a function of the number of transistors connected to an output called the fan out, and the technology. So this is just some internal parameter based upon what you're using as far as transistors go in technology. So when they say technology, don't try not to misinterpret that. When they say technology, you can just immediately replace that word with size. So if they say technology, they mean, are you using 14 nanometer technology? Are you using 32 nanometer technology? Are you using 55 nanometer technology? So that's what they mean by technology. Okay, so moving on. So typically the voltage was reduced about 15% per generation in 20 years. Voltages have gone from 5 volts to 1 volt, which is why the increase in power is only 30x. So that's where a lot of our power savings come from. Even though we did a lot of frequency scaling, we were able to make this switching from having to switch 5 volts from having to switch only a single volt, which is really, really good for us. Because we notice here that this is an exponential. We have this voltage squared term here. So it's very, very good for us if we make that number very small. Okay. So we do some calculations on relative power here, and this is basically just calculating power new, putting it over power old. So that's how we get relative power. So it's exactly how it sounds like. It's the power of some new relative to the old power, and then they plug the equations above in with the values they define. Okay, That makes sense. Okay, so let's see what else we have. Let's see what else we have interesting in this chapter. So the modern problem is that further lowering of the voltage appears to make the transistors too leaky. So that's a very interesting problem that we'll talk about in a research paper that I'll present sometime this summer. And it deals completely with this problem of leakage current. So it's all about how do we save power, but at the same time improve performance, because we don't want to be we don't want to be constantly leaking current out of these transistors. That's not good for us, because we're wasting there. And there's ways to mitigate that, but those have a cost associated with them as well. Okay, so to try and address the power problem, designers have already attached large devices to increase cooling. So water cooling CPUs, right? Or the big fans and heat sinks you put on GPUs. So that's what they're talking about here. Although there are many more expensive ways to cool chips and thereby raise their power to, say, 300 watts, these techniques are generally too costly for our PCs. Okay. Since computer designers slammed into Powerwall, they need a new way forward. They chose a different path from the way they designed microprocessors for the first 30 years. Okay, so then they have a couple of elaborations here. So the first thing is, although dynamic energy is a primary source of energy consumption in CMOS, static energy consumption occurs because of leakage current. So as it implies, static energy is what happens. Doesn't matter. There's nothing going on. There's no instructions being executed. Everything's idle. You're still losing power. Okay. So that's responsible for 40% of the energy. So that's still a pretty significant margin. So dynamic energy is the most, but static energy is still significant. So power is a challenge for integrated circuits for two reasons. So the first thing, it must be brought to the chip. Secondly, multiple levels of the chip interconnect are used solely for power and ground, and then power is dissipated as heat and must be removed. So we have to bring a bunch of power to the chip, and then we also have to get rid of the side effects of power. That's the problems. All right, I think this is fairly near the end, because now we're talking about single core processors versus multi-processors. So this is very interesting. So the power limit has forced a dramatic change in the design of microprocessors. Okay, and so figure 1.17. Here we go. This is a great graph. So here we have our performance increases. So early year, or our earliest time we're talking about is 1978, where we have a 5 megahertz, the AX11 780, where we have it at 5 megahertz, and that's our baseline normalized to 1. And then we have, let's see where we can find, here we go, the IBM Power Station here. In this range, we're increasing by 52% performance per year. But we notice a disturbing trend, and that's between, the 2000s here. So this is when Moore's Law started to fall off. And so, even though we get to like the Xeon 4, so this is back 2012, boosted to 4 gigahertz, we're still only year over year improving by 22%. So, we got some problems here. This heyday that we had of nearly 2 decades of doubling our performance per year, it's not happening anymore. So that's a concerning thing for us. But it also means that we have to be more creative with our solutions. Okay, so rather than continue to decrease the response time of one program, so this is saying that instead of making chips faster and faster and faster to do one thing, why don't we do 4 things at once, or 2 things, or 6 things or 8 things. So now we're referring to what used to be just regular processors. So now those are just becoming cores. And so now we're making multi-core microprocessors. So things like quad core, we've got 4 processors or 4 cores. Now don't be confused with a GPU. So GPUs have threads, and people say CPUs have threads. Now just keep in mind these 2 threads are not equivalent. The amount of you can't even compare the cores on a CPU versus a core on a GPU. So just putting that out there early. So never do that, because if you talk to someone that knows what they're talking about, it's not going to be a good idea. Okay. So moving on, in the past, programmers could rely on innovations in hardware architecture and compilers to double performance. So now it's becoming more important to have a holistic understanding of hardware and software, because, you know, writing a single-threaded program, something that's going to execute on a single core, you know, it's fairly easy. It's fairly easy compared to, you know, definitely compared to multi-core. So once you start dealing with multi-core, you have to deal with things like synchronization, and honestly, the hardest thing in computer architecture is synchronization. So the hardware-software interface. So now we're getting to this parallelism. So we've got this jet engine example where we have 4 things doing the same thing at once. So pipelining, which we'll talk about later, is an example of instruction-level parallelism, where we can execute multiple instructions at the same time. Okay. So why is it hard for programmers to write explicitly parallel programs? So the first reason is that parallel programming is by definition performance programming. So that makes it difficult. So if you ever wonder why, you know, when some app runs slow and you ever wonder why, you know, why haven't they fixed this and made it better? It's because when you're doing optimizations, that is a lengthy process. So it needs to be correct, the program. It needs to solve an important problem, and it has to have a useful interface to the people or the other programs that invoke it. And so ensuring these things just makes it, you know, it's really hard sometimes. So the second reason that is that fast for parallel hardware means that a programmer must divide an application. So this is another interesting problem. So not every application can be divided so easily. So you can think about, what if I needed to do 4 different operations like division on just different numbers? Maybe I just needed to do 10 plus 8, or sorry, I said division. Maybe I need to do 10 divided by 5. I need to do 18 divided by 9. I need to do 2 divided by 2, and I need to do 6 divided by 3. All of those instructions we can do separate of one another. So we can actually draw that out. So let's just do, 10 divided by 5, 6 divided by 3, 18 divided by 9, or whatever I said, and then 2 divided by 2. Oops, I didn't realize that was the end of the page. So, in this scenario, every single one of these things can be executed at the same time. Now, what if we changed one of these to a variable? So what if we did 10 divided by n, and we called this x0, and then in the next thing we had 6 divided by x0 is equal to x1. Then we had 18 divided by x2, or sorry, divided by x1 is equal to x2. And then we had 2 divided by x2 is equal to x3. Well, we can't execute all these things together anymore because we have to calculate x0, plug it in here. Then we have to calculate x1, plug it in here. We have to calculate x2, plug it in here. So we're actually, we can't split this application very easily because, you know, if we split the application here, this guy still can't execute. He has to wait for this to finish, which has to wait in turn for this to finish. Okay, so that's what we mean by it can be difficult to divide an application. It's a very good point. Okay, and then they do their own analogy. Okay. Okay, and then they reference Moore's law again. Okay. And okay, so this is just kind of breaking down what each section of the book is doing. Okay. So basically what we have is we've kind of introduced, so let's do a little recap. So what did we learn in this section? We learned that starting from the very beginning, we learned that CPUs are very different. They're not all born the same. So CPUs and servers and personal mobile devices, they all have very, very different. Actually, I can probably just go to the table of contents. Yeah. So first we learned about computers, and then we learned that, you know, when we're designing a computer, we want to keep very important things in mind. We want to build for the future with Moore's law. We want to look at ways to speed up the common case. We want to look at ways to do things in parallel, and all of those 8 different things we learned earlier. Then we learned, well, when I write a program in C or C++ or Java, you know, how does that actually get translated all the way down to the hardware? And so we learned that, you know, that goes to a compiler, that high-level language. The compiler turns it into assembly-level instructions, which are specific to that architecture. And then something called an assembler takes those instructions and turns it into machine code, which is ones and zeros. So under the covers, so we peeked under the covers, so we peeked a little bit at what's actually going on inside of a CPU. So that's what we covered there. In 1.5, we learned that there are many different ways to design processors and memory. We learned about how there are different technologies, such as the sizing, so 32 nanometer technology versus something like 16 nanometer technology versus 14 nanometer technology. Then we also learned that there are different types of memory. So there's DRAM and there's SRAM, and each of those have different we have technologies for building processors and memory. So we have things like DRAM, which is a little bit slower than SRAM, but is much more dense. Then we talked about performance, and so this is how do we actually quantify performance inside of computer architecture. So we learned about clock cycles per instruction. We learned about how to really break down the timing of instructions. Then we learned about the Powerwall, and so at the Powerwall we learned that the main problem that we're facing nowadays is we can't adequately power the chips that we're making anymore, and some of that is because of thermal considerations, and then another part of it is that the routing and the interconnection networks are getting so complicated. What did I do to Hip? I timed him out for a little bit because he was just spamming a bunch of emotes. Listen, it's okay. It's only 600 seconds. It's 5 minutes. That's fine. The C change. So in this section, we learned about multiprocessors. And so here we learned that we can't get the same performance that we did previously using single processor design because of the all the considerations that we said earlier. Then we didn't really go over much of this in the concluding remarks. But this stuff is mainly a review of things we already know. So what I'd like to do is we should go to the fallacies and pitfalls section of the text. So fallacies and pitfalls is John Hennessy and David Patterson, the authors of this book. One of their famous things is they basically coined the term in the architecture community for this idea of fallacies and pitfalls. You know, it's their bread and butter. They use it in everything that they publish, whether it's a paper or whether it's whether it's these books. So where's the actual section heading? This is fallacies and pitfalls. Okay, so it's a benchmarking. So that's just benchmarking the i7. Okay, fallacies and pitfalls. So this is the last thing we'll go over. So the purpose of this section of fallacies and pitfalls, which we found in every chapter, is to explain some misconceptions that you might encounter. So fallacies. And then we also discuss pitfalls, or easily made mistakes. So pitfalls are generalizations of principles that are true in a limited context. So a lot of times people will use them and extrapolate them to something huge when it doesn't relate that way. So first we'll start off with the first pitfall. So expecting the improvement of one aspect of a computer to increase the overall performance by an amount proportional to the size of the improvement. So the great idea of making the common case fast has a demoralizing corollary that has plagued designers of both hardware and software. It reminds us that the opportunity for improvement is affected by how much time the event consumes. So if we have something that doesn't, so here we go. So a simple design problem illustrates it well. Suppose a program runs in 100 seconds with multiply operations responsible for 80 seconds of the time. So 80% of the program is multiplies. How much do I have to improve the speed of multiplication if I want my program to run 5 times faster? So this is where we use the famous Amdahl's law. So this is going to be defined as so execution time after improvement is going to be the execution time affected by improvement over the amount of improvement plus the execution time unaffected. So 20% of this program, so 20 seconds of this program is unaffected. You can't speed that up. So 80 seconds is affected by some scalar value n. And so what we do is we can rearrange this into some form or fashion. And so what we find is, after we move this around, we want this to get to 5x, right? And so what we find is it's impossible. There's actually no way in this design problem to make it 5 times faster. There's no amount. So just because we can make one part of the processor infinitely faster doesn't mean that it will actually improve the rest of the performance by a compensatory amount. So here's a fallacy. Computers at low utilization use little power. So this is actually not true. So warehouse scale computing is 10% and 50% most of the time, and 100% less than 1% of the time. So in this case, and the best result is still using 33% of the peak power at 10% of the load. So, just because we're not doing much as far as computation goes, we still have all the static power. And we saw from that figure earlier that static power is roughly 40% of power. So we can't get rid of 40% of power. It's only this 60% that is a result of switching or actually doing things. So another fallacy: designing for performance and designing for energy efficiency are unrelated goals. So this isn't exactly true. So the more work we have to do means that the more energy we're going to be spending. So they're not entirely unrelated. So pitfall: using a subset of the performance equation as a performance metric. So, we saw this already earlier, and this is basically that if we only use a subset of the performance equation, we can get a number that makes something look good in a limited context. But we don't want it in a limited context. We want it in its full performance metric context. So something like Mips. Mips is it's a very simple metric. It just is million instructions per second, right? So it's how fast can you do 1 million instructions. So here's the 3 problems that we have with Mips. So first, it specifies the instruction execution rate, but it doesn't say anything about the capabilities of the instruction. So if you can do 1 million instructions, that's great. But are you doing 1 million loads? Are you doing 1 million stores? Are you doing 1 million adds? So it doesn't take that into account. So second, Mips varies between programs on the same computer. So a computer can have a Mips rating. Mips is something that's also determined by whatever the what am I trying to say? The intrinsic nature of the program. So if a program has, very low latency instructions, say it's all adds, it's 1 million adds, that's going to be done very quickly. But if we start doing a bunch of loads and stores, all of a sudden we're using a memory subsystem, and that might take a while. So the third, where's the third? So here we have first, then second. Okay, finally. And most importantly, if a new program executes more instructions, but each instruction is faster, Mips can vary independently from performance. Okay. So yeah, we see that it's important that we look at good performance metrics, and we use them well. So that's a pitfall. So not all performance metrics are the same. And so yeah, these final remarks, this is going to be just this big picture idea that execution time is the only valid and unimpeachable measure of performance. So how fast it takes to get from point A to point B, that's the only good end result. If you have, some novel idea that improves something, and you say, oh, my performance is better, the user's not going to care. So let's say you're talking to someone, and they say, we made this one thing 1,000 times faster. And then you run your application, and it takes, maybe it's 5% faster, they don't care that you made it 1,000 times faster. To the person running the application, you only made it, 5% faster. Okay. So let's see. Let's see what the best way to kind of break up the rest of this book. So if we want to learn about data path, it's going to be 3, 4, 6. Control is going to be 4, 6, and appendix B. Memory is 5, input is 5 and 6, output is 5 and 6. So what we'll probably do, we have to start with arithmetic, which is chapter 2. After chapter 2, we'll probably go through appendix B next to try to understand data paths. And then we'll go into 3, 4, and 6. And then we'll probably find a clever way to do the crossover between data path and control. That's going to be a very fluid transition. And then same thing with the 6, 6, and so chapter 6 on both of these, input, output, so I/O, and control and data path. And then memory will kind of dedicate to itself. So the only reason why they have chapter 5 here for memory and input and output is because memory mapped I/O. That's likely the only reason. Or maybe RDMA as well. Okay. Great. Well, that was fun. We got about 2 hours of good teaching in. I appreciated that. We doing anything else? Anything else fun? I don't know if anyone's actually still here, or if people are just asleep with the stream on or something. I don't know. Alpaca. Okay, guys. So that's going to conclude chapter 1 for us. I think we learned a lot about, the basic architecture of a computer. We learned a lot about layers of abstraction, and then we also learned about the fundamentals of what we need to do in order to design for the future. Okay. So there's 2 people not asleep, it seems. Well, that's going to do it for us today, though. So, likely tomorrow, we're going to have another stream. We're going to try to get through chapter 2 tomorrow. So, hopefully, we'll get through this book in roughly a week. We'll try to do about a... Hopefully... Oh, great. So, hopefully what we'll try to do is go through, one of these books. Yeah, absolutely. I'm happy to do it. So we're going to try to go through one of these books a week or so, depending on how many chapters it is. So this first one, we're going to do Computer Organization and Design, which is this book right here. We're using the RISC-V edition. So RISC-V... Okay. Yeah, listen. Part snack, part AI. Well, hey, there's nothing wrong with that. AI is pretty cool. A lot of people misunderstand AI. They think that AI is some mystical, magical thing, but all it really is a bunch of linear algebra. So, a bunch of convolutions. Even perceptrons. Perceptrons aren't extraordinarily difficult or hard to understand. The Google's TPU, the Tensor Processing Unit, Now, basically the only thing that the tensor processing unit is a giant matrix multiply and accumulate unit. It has a giant matrix multiply accumulate unit, and it has pretty good memory bandwidth, and so that's why that kind of explains what AI is. So all AI really is a bunch of matrix multiplications and operations like convolutions. Well, like I said, this is gonna conclude it for the stream for today. So if you need anything else, hey, join us sometime tomorrow. Which way did he go? Okay. If you need anything else, join us tomorrow. We're going to be going over chapter 2 in this book. Let's go ahead and put it on that chapter now. So I think this is historical. Yeah, this is the history of computers. There's a lot of interesting stuff in this book, but not everything is relevant. Okay, yeah, instructions. Oh, it starts in instructions. So it goes over hardware, RISC-V. Okay, so, it talks about, I get it. Oh, okay, are you guys, okay, well, have a wonderful time. Thanks for joining us. Just talked about AI today, or yeah, machine learning is not particularly difficult. Yep, no problem. So I would say tomorrow I'd like to do it probably sometime tomorrow evening. I might do an early morning, so I'm in Eastern Standard Time, so I'd like to probably stream sometime in the morning. And then also sometime in the evening. So when I mean evening, probably 6 p.m. EST, and when I mean morning, probably sometime around, I would say probably 8 to 9 a.m. EST. So, as always, thanks for joining me, and go out there and go learn something new. Ciao.